that the horizontal and vertical movements happen independently of each other. Vertically, the object is affected by gravity, causing it to accelerate downward, which you can see in the curved path it follows. Horizontally, however, there is no acceleration, so the object moves at a constant speed. This means the horizontal distance covered is uniform with time, while the vertical position changes due to gravity. Together, these independent motions combine to create the curved trajectory of a projectile.
The horizontal component of motion shows that there is no horizontal acceleration, meaning the horizontal velocity remains constant throughout the motion. This is represented by the equation where acceleration in the x direction equals 0. Because the velocity doesn't change, the displacement in the horizontal direction can be calculated simply by multiplying the constant horizontal velocity by time. It's important to note that this assumes air resistance is ignored, which means the horizontal velocity stays the same during the entire flight. This principle helps us understand and predict the horizontal movement of objects in projectile motion.
Here, we focus on the vertical motion component, where the initial vertical velocity is 0, meaning the object starts from rest in the vertical direction. The vertical acceleration is due to gravity, which acts downwards with a constant value g. Using the equations of motion, the vertical displacement after a time t is given by 1/2 gt squared, reflecting the increasing distance fallen over time. The instantaneous vertical velocity at any moment is simply gt, meaning it increases linearly as the object continues to fall. Essentially, this vertical motion mirrors the behavior of an object being dropped straight down without any initial push. As we continue, let's focus on how displacement relates to time when an object falls. The displacement equation from SUVAT is SY equals half times gravity times time squared. If we take the height of a cliff as the displacement, we can substitute that into the equation for h, which leads us to express time as the square root of 2 times height divided by gravity. This shows that the time it takes for an object to fall depends only on the height it falls from and the acceleration due to gravity, not on any other factors. This is really important to understand when analyzing free-fall motion. Here, we see how the horizontal range is calculated by combining horizontal velocity and the time the object is in the air. The base equation shows that distance equals horizontal velocity multiplied by time. To find the time, we use the vertical motion formula, which involves the height of the cliff and gravitational acceleration. Substituting time into the horizontal equation, we get the range as the horizontal velocity times the square root of 2 times the cliff height divided by gravity. This tells us the range depends on how fast the object moves horizontally and how high it falls from, illustrating the main factors affecting the distance traveled before landing. As the object moves through the air, its horizontal velocity remains constant because there's no force acting horizontally in this scenario. The vertical component of the velocity, however, changes due to gravity and can be found by multiplying the acceleration due to gravity by the time elapsed. To find the total velocity at impact, you combine both the horizontal and vertical components using the Pythagorean theorem, since the components are at right angles to each other. This gives the magnitude of the velocity vector. To determine the direction of this velocity relative to the horizontal, you use the tangent function, which is the ratio of the vertical component to the horizontal component. It's important to always express the angle relative to the horizontal